in the patient body. But the structure is somehow different from we saw in the previous example, because when the X-ray enters the body, first of all, it may encounter with the skin and then encounter with the fat under the skin, and then, for example, muscle, bone, and after that. So there is many different type of tissue in the way of X-ray when passing through the patient body. So the formulation can change somehow different. Here, which we have the attenuation value and the thickness value should be changed slightly by such a formula. For example, mu1 by x1 plus mu2 by x2, mu3 by x3, and so on. So, the first picture that we start this course with that, the X-ray source and the body and the detector, we can somehow simulate by this sketch. There is different type of tissue that X-ray should pass through, and in each tissue there is different attenuation values, and then at last, after passing through different tissue, we have a transmitted photon flux. And as I said, because of differentially attenuation of the X-ray in the anatomical structure, we have an image that somehow is the shadow of the internal organs. We can call the X-ray image as the shadow of internal organs. The X-ray image is a shadow because it's formed by different transmission of the photons in different points. And it makes the image, and as I said, we call the image as contrast, because the image means contrast, or contrast means image. These two terms are somehow equal. Everywhere you have contrast or different in colors, you have image, and everywhere you have image, you can see different colors or contrast in colors inside the image. So what we see in an image is contrast. And here, as a summary, we can say that as X-ray is sensitive to value of density and atomic number, and we have different density and atomic number in different point of body, so we have different value of photons passing through, and then we have different colors in the shadow, so we have image. This is the chain of the X-ray imaging. I explained about the X-ray attenuation. Now, let's go through to X-ray production. How X-ray produced in the X-ray source. What is the photons? Photons, especially in terms of physical demonstration, is electromagnetic wave. The photons are electromagnetic wave. Here is visible light wave, is a big wave, and this is the X-ray. Photon, like a small wave. And if we have an atom like this, the smaller one can easier pass through the atoms compared to larger one. Because of that, the visible light cannot pass through the hand, and the X-ray photon can pass through. So, In terms of wave, we can say that the X-ray is a smaller wave, electromagnetic wave, and the visible light is larger magnetic wave. In terms of energy, we can say that X-ray is high energy photons, and the visible light is low energy photons. So we can define them in both sides. In electromagnetic, in context of electromagnetic wave, like this, and the context of energy. Both is correct, and everywhere we need one of them, we can use it. How we can produce the photons? Most of the time, when you want to make photons, the visible or non-visible photons, it needs to change the type of energy. For example, somewhere we change the thermal energy to visible light. Somewhere we change electrical energy to visible light. Somewhere we change the electron energy to light. Different type of methods. But most of the time, to make the light or photons, we need changing the type of energy. For example, in this slide, we change the electrical energy to photons, for example. When you heat a metal, for example, iron, I think you saw in the movies, when the metal make very, very heated, it generates a red light, yes? It's some kind of changing the thermal energy to visible light. How we can generate the X-ray? Again, by changing the energy type. In this method, we have very energetic electrons, the electrons which are normally rotating around the nucleus in the atom, and convert the kinetic energy of electrons into the photon energy. How we can do that? First of all, we need a source of 3 electrons. How we can find 3 electrons? And then accelerate the electron to very high speed, make the electron to move very high in very high speed, and then suddenly stop the high accelerated electron. Make a free source electron, then accelerate it in, and then stop the electron suddenly. The kinetic energy of electron should be converted to another type of energy, for example, heat, visible light, or other types of energy. Here is a schematic of the X-ray source. We have a cathode, we have an anode, a vacuum tube, and a high voltage that's applied between these two parts, the cathode and anode. How it works, we have a cathode that generates free electrons. There is an anode here in front, the target of incident electrons. Why we use a vacuum? Because the path for electron should be very clean, because if it was not vacuum, there may be some particles, some dust, and the way of electrons are not free and clean for movement, and a generator which apply a high voltage. As the electron has minus, the electron has minus polarity, as you know, electron has minus polarity. And if you put the electron between voltages like this, the minus and plus, the minus repel the electron and the plus attract the electron. So the electron start to accelerate. Because the minus repulse the electron and the plus attract the electron, so in the polarity of the minus and plus, the electron will move. We call it anode, and this is cathode. So we need a high voltage, we call it generator. We need a vacuum tube, a very clean vacuum tube, a cathode and an anode, an electron which is accelerated, and when the electron hit the anode surface, it suddenly stopped, and the kinetic energy, the motion energy of electron converted to, heat and radiation. So another picture of the X-ray source. There is a heated filament. When you heat a metal, it will, make lights and make free electrons. Using a high voltage between anode and cathode and anode, the electron accelerated, start to move very fast, and then when they reach the surface of the target, then they suddenly stopped, and the kinetic energy of the electrons converted to emitted X-ray. And so we use this X-ray for imaging. Here's a picture of cathode, which are some, spiral shaped metals, which is heated by flowing the current inside it. And when the filament heated, the electrons from inside of metal come out of the filament body, and there is a cloud of the free electron around it. A cloud of free electron around it, and so we have a free electron ready to accelerate. For example, the tungsten metal is very appropriate for this, for making the free electron. When the tungsten filament heated to 2000 degrees centigrade, it heated, and as you know, in the metal we have a very large amount of free electrons. The free electrons inside the filament get energy and go around the filament, and so we have free electron ready here to make it accelerate. What about the anode? The anode is a metal, a barrier in front of electron. Here we have free electron. When you apply the high voltage, the electron start to accelerate, and then when they reach the surface of anode, they interact or hit the anode surface. This is a real picture of the anode inside the X-ray source. So the electrons here has very high speed, around half of the light speed. So it's a very high accelerated energy here. When the high energy electrons hit the anode surface, what happened? The energy converted to electromagnetic wave. Most of the time, when a very high speed materials suddenly stopped, the electromagnetic wave is generated. Most of the time, it's heated. Most of the time is heat, 99% is heat, and 0.5% to 1% is X-ray. So the efficiency is very low. At most 1% is the efficiency, and somehow we have a small amount of X-ray photons that is generated by accelerated electron. So, you know, the structure of the X-ray source is very complicated. We don't want to go deep inside it, but what is important for this class is there is some parameters that should be adjusted in X-ray source. For example, when you want to make image of the patient, if the patient is fat, you need higher number of photons. If the patient is thin, or for example, you want to doing a pediatric image, you image a child, or image a small part of body, for example, hand, compared to abdomen. So it needs to design the energy and the intensity of photons. The value of X-ray photons is not same for thick people compared to thin people. You should adjust it. How we can adjust the value, the number, and the energy of photons come outside the X-ray source? The first thing is we call it current, or MA. MA is abbreviation of milliampere. What's the definition? The amount of electrons hitting the anode, and consequently the amount of emitted photons. So if we want to increase the number of photons come outside the X-ray source, we change the MA, or we change the number of electrons is accelerated. So the first thing is MA. The second is kV, which is abbreviated to kilovolt, is the energy of electron. Consequently, the energy of photons is higher at this situation. For example, let's compare these two conditions. This is X-ray source. It gives us X-ray photons that come out. Let's compare these conditions. We have 3 photons, for example, 3 photons, 10 keV energy, 30 keV energy, and 50 keV energy. Situation 1. Situation 2 is 2 photons, for example, 100 keV and 120 keV. Situation 2. In situation 1, we have higher number of photons, but the energy of them is low, compared to second situation, in which we have only 2 photons, but with higher energy. Here we have high quantity Here we have high energy, but low quantity. But low quantity. It means that we can control the quantity or number of photons. We can control the energy of photons. Both of them can be controlled by the user, which is operate the machine. When you look at the panel of a radiography machine or panel of the mammography machine, you can see that the operator of the machine should adjust the MA, which leads to photon numbers, KV, photon energy. And they should be adjusted. And the third item is time. For example, in adjust to 1 second, for example. The duration of imaging process is, for example, 1 second, 2 seconds, 0.5 second. So X-ray tube and the generator provide the ability to have a range of tube voltage to control the energy, tube current to control the number of photons that will contribute in imaging process, and the exposure time in second is the time of the imaging. And let's sum up the quantities here. So we have three main parameters in X-ray measurement. The first is beam quality. What's the meaning of beam quality? Beam quality is penetratability. How much the X-ray can penetrate the body. It depends on the energy. As the energy of photons increase, it can better transmit the material. It can better pass through the material. We call it penetratability. It depends on the energy. How we can change the energy of photons by changing the KV of the X-ray tube in the panel, in the operation panel. The second is X-ray beam quantity. What's the meaning is intensity. Intensity is number of photons. The first one was the energy of photons. The second is number of photons. How many photons is generated and is used to go through the patient's body? The number of photons. How we can control the number of photons in X-ray tube? By control the MA mostly. But when you change the KV, you can change the number as well. We need to, based on the patient thickness, patient body size, based on the type of disease we are going to make image to diagnosis, we should design the energy and number of photons. And there is a very important parameters called exposure. Exposure is somehow mixture of quantity and quality, because it means that how much energy we are using to make image, how much energy, which is somehow multiplication of or addition of number of photons and the energy of photons. Or we can say that the energy flow. Okay, I think it's enough for the first session. I think the second session will start in 10. We can start in 10:15. Okay, 10:15. Okay, thank you.